Session. So next we'll have a session from Dr. Soumyajit. He is currently the head of CCDS at IIT Kharagpur. He did his BE in Electronics and Telecommunications and Engineering from Jadavpur University at Kolkata. He did his master's and PhD degree in Computer Science and Engineering from IIT Kharagpur. And he joined as a faculty in the Department of Computer Science and Engineering in 2013. So he leads the High Performance Real-Time Computing Laboratory, or HIPRC, in Computer Science and Engineering Department. His research interest include autonomous, trustworthy cyber-physical systems, formal methods, real-time scheduling, and GPGPU optimizations. He has published many papers in around 90 international conferences and journals, including top tiers and A-star conferences. He has served as reviewers in many IEEE and HCM transactions and PC members in reputed conferences like DAM, DATE, RTSS, ICCPS, and so on. He has organized special sessions on CPS in DSD since 2020 and also in 2021. He is the winner of the Best Design Award in VLSI 2006 and has an honorable mention in VLSI 2007.
Thanks, Sujita. I hope I am audible. In Teams also. Okay. Fine. Then let's start with this session. So as Sujita said, I do a few things on GPU. Actually, I don't do anything. Basically, the students who do it. I take the classes. And initially, I used to do, but nowadays it's mostly them doing it. So anyway, let's focus on the problem at hand. So we'll try to give a snapshot on the CUDA programming model. But first of all, what CUDA is? Let's understand. So CUDA is a programming infrastructure. It's an extension of C as defined by NVIDIA for programming the NVIDIA GPUs, right? So that also means that you will need to understand the beat of the GPU architectures, right? So that we know that what is the platform on which we are doing the code. There is a lot of feedback in the. Okay. So we have several topics to cover. Initially, we will talk a bit on what are GPUs, what is the basic architecture, and then we'll introduce the CUDA programming model. We'll talk about the different constructs where CUDA will differ from C, and we'll try to do that through a example. And finally, if time permits, we'll go to some of the advanced programming concepts. So take this just as an introductory part on CUDA, and after this, we'll have a lab session where we will introduce some online programming tools using which you can practice GPU programs on GPUs that are available in the cloud. And in any case, if you are really interested into GPU programming, we also offer a full-fledged 30-hour lecture course in NPTEL called GPU Architectures and Programming. You can learn from that. So first of all, what are GPUs? So GPUs are essentially they are an evolution of parallel architectures that have happened over time. So it's not that NVIDIA were the first people who talked about parallel programming and parallel architecture. So before that, people have been trying to do that. Okay, so people have got these concepts of vector processing. Like, so the idea with these vector processors was that you will have computers, you actually had computers in the 80s who supported, I mean, addition or subtraction or any kind of operation over vector data instead of just working on scalar data. So those kind of instructions were supported in earlier architectures also, but we call them with a different name, vector architectures. In fact, even in Intel CPUs, there used to be this support of what we call as multimedia extension or AVX instructions. So the name that was used was different. It was called SIMP, that is single instruction, multiple data. So as an example, instead of just doing, let's say, add X and Y, think that X and Y are vectors of size 10. And I give an instruction to the computer, add dot v. So it's a vector add instruction. And I ask it to add two vectors. So it means that with the same instruction, let's say there are vector registers. That means instead of two integers being stored in registers, there are vector registers, each of them containing a vector of data. And I am doing the addition in one step on the full vector and reporting it out. So that is the way it works. So all things. Yes. Is there anybody speaking on the Teams? Okay. So this is the idea with which people talked about this vector process. So they would have this kind of vector register, and also that would mean the functional units. For example, I talked about vectorized addition. So you need the hardware to support that, right? So there should be a adder circuit on the computer, which not only will do simple addition, but it should also do the vector addition, right? So all that support should be there. So there was this idea of MIPS, which was one of the first CPUs that the computer designers configured. And there was this vectorized version called vMIPS. Okay, so basically that was one of the earliest propositions of vectorized architectures. Am I audible in this? Right? Even if I correct this, I'm audible, right? So I can use better. Okay. So with this idea, I will just give you an example here, like how a vector processor will look like. So let's say I have two large vectors. So these are 10 size vector in an array and another array B, and I want to add them. So just think in terms of the hardware. There is only one adder to do the addition. Okay, the adder does addition of two scalar components, one in each one clock cycle, right? So in that case, this entire addition and producing an output vector C of size 10 would take 10 clock cycles. But then instead of that, if I have this kind of parallel addition units, okay, then I can do the addition faster, right? So maybe my talk will look a bit different from the others because there was purely the software perspective you may have got. I'm coming from the architecture side so that you understand. Yes, you have a question.
Speaker is that's quite speaking in the mic. Speaking in
Sit there in the Teams.
yes.
In this room, everybody can hear. Yes. Then that's fine. Okay. So all I'm trying to talk about is how parallelization really works in terms of the hardware. Because you see, the hardware amount is finite. I don't have infinite hardware. Like I want to add 1 million size vector with another 1 million size vector. I cannot expect that it will happen in one cycle, right? So it depends on how many cycles each of the hardware units will take and how many such hardware units I really have in the system. Okay. Why am I saying this? Because suppose tomorrow you want to do machine learning in a GPU and your GPU actually has got, let's say, 32 adders like this, right? So it only can do 32 addition operations, including point or integer in parallel, right? It cannot do more than that. So those are the limits of parallelization architectures have. And if you are aware as a programmer, then even before writing your code, by analyzing the algorithm, you can have an idea how much parallelization you can really have. What should you expect from the hardware? You can understand that. And accordingly, you can choose how many GPU cards to really use. Right? So if you want to be a good parallel programmer, you have to understand the architecture in a better way. To really understand that well, how much, what to expect from it, how much is the performance required. And this is very important for the user community in general. So I am just starting from that point. Now coming to a basic GPU, as you can see, there are many things here. We are just showing the picture. Of course, explaining all the points will require a lot of background. What I'm trying to say also, this is a GPU architecture of let's say 12 years back. Okay, so nowadays things are anyway much more advanced. Okay, so what I'm trying to highlight here is, you see, there are a lot of parallel processing units available inside a GPU, which you are anyway exploring. So all these small things you see with the label given as SP, it means a scalar processor. What it really is basically a simple integer ALU pipeline. That means the number of SPs that you have or scalar processors. For users, we call it CUDA codes. People understand this better, CUDA codes. But if you are a computer architect, you will think that, well, this is a scalar processor. These scalar processors together make what we call it as a streaming multiprocessor SM. Many such streaming multiprocessors together give me something called a thread computing unit. Okay. And they together again are connected by a network. And then there is a connection to the cache memory of level 1, further going to a shared memory or level 2 cache. And then there is a connection to the global memory like that. Okay. So it's a complex thing. When you use a GPU card, you think, I mean, there is some CPU inside this cabinet, computer cabinet. You have a motherboard on which you have a CPU chip, some DRAM chip, which we know that if you just open the cabinet, you can see those things, right? And if you want this to support, to have a GPU, you have to buy a off-the-shelf GPU card from NVIDIA or some other company. On the motherboard, there will be some PCI slot through which you can attach it. Now, on that GPU card, what you have is something like this, okay? So on that GPU card, you have two primary things. One is the DRAM. So the GPU has got its own memory space, which is different from the memory space of the CPU. This is something very important to remember, because we use this knowledge when we talk about the GPU. Okay. So from this point, the key takeaway is very simple. We need to understand that there are a lot of CUDA cores or scalar processors, which are the unit of computation in a GPU. Okay. Now, what they can do integer arithmetic. Okay. But let's say you are doing some complex calculation, scientific calculation or ML calculation. You also need what we call as floating point arithmetic. Does everybody in this room understand what is floating point arithmetic? Right. So on digital hardware, I can do it using fixed point or floating point. Floating point arithmetic allows you to choose the precision like you want, right? So in GPUs, you expect there are specialized floating point units, both in 32-bit precision and 64-bit precision. If you are training large deep learning models, you need support for floating point arithmetic, because that is the go-to operation in a large deep learning model. So the more number of double precision, that means FP64 kind of hardware you have in the GPU, is the better the GPU will be with respect to the parallelization. So like I was saying, that it contains, so this was a picture of a very old GPU actually. It is a small GPU, GeForce 8800, pretty old, outdated one. The time around which maybe I have made the first version of the slide. After that, I didn't change the picture. But anyway, the concept remains still the same. And I think still this is a good slide, because the complexity is still lesser than what we have nowadays. And this still should be a starting point. So what we have is many, like I said, scalar processors. They are organized like these streaming multiprocessor SMs. Many such SMs, you can see they have got some internal memory here. Many such SMs together give you what we call as TPC,
thread processing units, and many such thread processing units together represent the full computing power of one GPU. Okay. Now, how did GPUs come? We'll cover this very fast. I will skip over certain things. What we are trying to say here is that, well, people initially did not make GPUs for day-to-day usage. If you look at the name, it's graphics processing unit. So people wanted to accelerate the way graphics is displayed on the screen. Okay, so for displaying the graphics on the screen, what do you need? You need some internal hardware different from the CPU, which is continuously refreshing the pixels on the screen, right? What is basically the screen? Screen is an output device, like a printer. What does the CPU think of the screen? The CPU thinks of it as a 2D array. That's all. The CPU doesn't care about anything else, right? And there is something called the ray tracing hardware inside the CPU, whom the CPU just populates that 2D array with data, RGB data, and that ray tracing hardware is going to paint the screen, right? So that's the purpose. People wanted to accelerate this computation. So that was initially from where the idea of graphics pipelines or graphics processing units came up. People tried to think that, well, you see, by default, painting a screen with various colors, pictures, etc. When do I need to do it very fast? I can paint the screen with color update slowly or fast, right? But when do I want it to be very fast? If the picture that I am showing is very dynamic, then where is it dynamic? In a fast video game. Need for speed. Road rash. I don't know what you play nowadays. That's what we play. Okay. So the modern video games have got very realistic stuff, right? And also nowadays you have virtual reality and augmented reality, where you have all this much more faster dynamic generation of image data coming up as a real requirement, right? So people wanted to accelerate that operation. But one thing people realized when they wanted to build this hardware, that say graphics is only parallel. There, I mean, I have to paint the point here, I have to paint the point here, and I can do them in parallel. There is no dependency. So that is why I can have many scalar processing units which are stitched together in a hardware, and they can do the job. So then why do I make a custom hardware? I don't need to make a custom hardware. Take a usual computer's standard ALU pipeline, which people already know how to design. Take all those pipelines, put them together, and make a simple circuit where you have many such integer pipelines together, thousands of them. That's the GPU, right? Now the point is, since these are all very basic computing pipelines, right, for which historically computer scientists have written compilers, so that somebody can write a C program, the compiler can compile, and that program will run on a single integer pipeline. So that idea was quite easy, right? But what is the difference now? The difference is that instead of the program being running on one integer pipeline, the program is running in parallel on thousands of such pipelines, right? So that's the big difference. But the issue is, this means I can program a GPU. Unlike typical hardware, whom once you said that it is done, the hardware will do only one job, but the GPU is a programmable thing. That means you can write one program and make the GPU do one computation, or you can write another program to make the GPU do another computation, right? So it is just like a CPU, but a parallel programming computer, right? So people say that, well, these are not just the graphics processing units, right? But they are what we call as GPGPUs, general purpose graphics processing units. That means I need not only use them for updating the display of a computer, but I can use the GPU for general purpose computing, where I have a lot of parallelism in my requirement. If I have such a requirement, I can use the GPU instead of using a CPU. So with that idea, GPUs became very popular. Okay. So these parts will speak on what is the graphics GPU, etc. And we'll just go forward to this general purpose computing. So typically, some of these older GPUs, like we said, they have got many such scalar processors. But the other important thing is, where you understand, having many scalar processors together does not end the story. Because if I have to do 1000 addition operations in parallel, I need to fetch those instructions and feed to the pipelines, right? So just having the 1000 ALUs together won't help. I need to have those pipelines. That means instruction fetch has to be in parallel. Only if instruction fetch is in parallel, then I can decode the instruction in parallel. Then I can execute them in parallel, right? So I should not only have such processing ports where I just have the ALUs, but I should be having many multiple instruction fetch units, multiple instruction issue units. That means what I'm trying to say is, in such a processor, apart from having many ALUs, I need to have many instruction fetch units, decode units, etc., etc. Now, we understand a bit about what is there inside a GPU. There are many such units, etc. I just talked about. But then, how do I execute? How do I execute code? So here, they said that, well, earlier people talked about SIMD. When people were talking about vector processors, they had single instruction or data. But let's generalize it further. That means, you see, I am not talking about just executing one instruction with vectors. Okay? That means I'm not only going to talk about SIMD, but rather what I really have is many threads are executing in my program. And I want all the threads executing using single instructions at a time. Is my point taken? What I am saying is, in a GPU, what do I really want? Do I want it to execute one vector addition and then some scalar code? Then maybe another vector addition or vector subtraction? No. I will like to generalize it. That means all my instructions are vector instructions. Unlike the CPU, the GPU is a computer where every instruction is a vector instruction. So I launch, let's say, to the power 10 threads. And I am computing in parallel over to the power 10 threads. At every clock cycle, this is the hardware where I am executing one vector instruction over all the to the power 10 threads. Now one may question, well, how will this work? Because at any point, are there really such applications where every thread will require the same instruction? There are such applications. For example, let's say you are processing an input image, okay, and you are doing a thresholding. You are trying to convert a colored image to a black and white, right? So every pixel you want to threshold, you want to compare with the threshold and decide on a grayscale. That's all, right? So all operations are indifferent. So first operation is to take as input the pixel value. Second operation may be to apply a filter. Third for noise rejection. Third operation may be to compare with the threshold. Fourth operation may be based on the previous comparison, apply a black value or a white value. Right? So you see all these operations that I talked about in sequence, they are all happening on all the threads in parallel. Right? So all the operations can be vector operations and they are happening in parallel. They are happening in parallel in lockstep on all the threads. That means at a time all the threads are executing one operation. Okay. This is what I mean by lockstep operation. That means only when all the threads execute one operation, then only the threads will go to the next operation. Okay.
I have a basic question. Like you have said, GPU designed to do vector operations, right? So what is the basic difference between a scalar and a vector operation? Like, is it vector operation means to adding two arrays together, something like?
All your variables are vectors. I think your question will be answered when we show you some example. Okay. For the time being, just believe whatever I am saying for the next 30 minutes. Okay. We'll come to the questions after we display them. Okay. So with this background, we will go to some program examples from which we'll see how it works. So And once that is done, we'll come back to this architectural details. So for the time being, I mean, whatever slides I have skipped,